Hi everyone, and thank you for attending the presentation we will be giving today. Before jumping right into it, I'm going to introduce Accenture's team present today in this session. I am Maria, and in the call with me we have Roman and Guillermo, all of us part of the Accenture Applied Intelligence Center of Excellence based in Barcelona. To give you a bit of context and let you know where we'll land within Accenture, our team is part of the Accenture's Global Applied Intelligence Network, as shown in the current slide, and we are focused on anything related to supply chain and operations, going from procurement to last mile delivery. The team is composed of more than 4,000 data scientists working across more than 20 industries, and we are experts in different areas and capabilities. One of these concrete areas of specialization is operations research, in which we develop projects that might include any simulation or optimization technique, such as discrete event simulation. And as we can see, only in our Barcelona team, there are approximately 30 people trained in SIMIO, working closely with multiple clients requiring simulation models to take data-driven decisions on their day-to-day businesses. The model that we will be presenting today is a production plant simulation model that we developed for a food processing company. The client objective was to improve a concrete area of the production plant in scope. Concretely, the model tests different scenarios to understand potential ovens management improvement by optimizing loading and unloading shuttles movement. In this use case, the model was developed in SIMIO. It was integrated in their environment, and all the results were reported through a Power BI dashboard, as we will be seeing. As shown in the slide, the best case scenario that we showed to the client and that we defined as the best option that they could go for had a potential 12% SLA improvement compared to the current baseline logics. I'll now hand over it to Guillermo so he can demo and give you the technical detail about the mentioned production plan model, and I hope that you enjoy the presentation. Thank you very much.
Hello everybody. During this session, I'm going to present you a solution to improve food production operations using SIMIO. Food production plant digital twin is a tool aimed to achieve a capacity increase in Accenture's client systems and to avoid capital expenditure by achieving throughput targets from existing assets and optimizing the system to use fewer resources. The main goal for this client was to improve ovens management by optimizing shuttles movement. For this to be complied, a digital twin was designed and implemented in SIMIO to replicate the plant area in scope. This is the facility window, where the plant layout and all objects in it have been represented. There are also included multiple KPIs that are audited during the simulation and that allow the user to track different metrics. such as ovens and shutters resources states, the number of available ovens at any moment of the simulation, the product backlog at the beginning of each one of the production lines, the average utilization for each one of the shutters, and their coordinates. The model configuration will depend on the chosen parameters at the beginning of the simulation. These parameters are included at the Properties menu on the right part of the facility window. As seen in the simulation visualization, product is arriving through three different production lines, L1, 2, and 3. Then, group of 5 product cubes are placed in one pallet in the combiner. The pallet is then picked up by the drop-off shuttle to be carried to the closest available oven. Finally, the oven proceeds with the cooking action, and once it has been cooked, the product is transported again to the corresponding drop-off line by the pickup shuttle. To give a bit more detail on the model implementation, the crane and the bay objects are used to replicate the movement and logics of the shuttles without them crossing each other. The bay allows the simulation to prevent a deadlock situation by pushing an idle crane by the other and it to pass. As an example, if the drop-off shuttle is idle at oven 5 after after unloading a pallet into it and the pickup shuttle needs to go to, let's say, oven 2 to load an already cooked pallet, the drop-off shuttle will be pushed to a point further to the right so the pickup shuttle can reach oven 2. In order to make the model scalable to any other client production plant, it is fully data-driven, and objects on the facility window are created using auto-create tables. There have been used 10 different input tables during the simulation. 3 arrival tables, one for each product type. One table to assign the oven's priorities depending on the chosen scenario. Another 2 tables to create all the objects and nodes in the facility and to assign their corresponding properties. 2 additional tables to replicate the ovens and shutters failures to validate the baseline model. One table to specify the possible destination nodes for the pickup shuttle. And the last one, the work in progress table, which, as we will see later, it is used to indicate which ovens are busy at the start of the simulation. Model results are recorded on different output tables that, later on, are visualized on a Power BI dashboard. Let me fast forward the simulation to record data. Okay, I think it's enough. The main information obtained from the simulation covers shutters recorded failures and the time they have been fixed, shutters loading and unloading operations, daily ovens and shutters utilization and the amount of time they have been idle or down, oven cycles to understand their workload assigned to each one of them, recorded product arrivals and the time it has passed until they have been picked up by one of the shutters, pallets timing system, shutters coordinates to track their movements, shutters picking operations, and 3 output tables to track the product backlog at the beginning of each one of the production lines. Although most of the model's logic is implemented within the objects, several processes have also been created. One of these very interesting is the one we launched at the beginning of the simulation. In this process, on the one hand, a search step will be used to check in the working in progress table that was shown before which of the ovens will be busy at the beginning of the simulation. Then, the products that are being cooked inside of the ovens will be created, and the corresponding remaining processing time will be assigned. Using the model, the user will be able to create some scenarios, and one of them allows the user to decide how many ovens should be operational. Then, on the on-running initialized process, the model checks how many ovens should be working and the rest of them are set as not available. As an example, if you want to study the feasibility of operating with 9 ovens at the beginning of the simulation, oven 10 will be made not available. Most of the rest of the processes are used to record metrics during the simulation in the output tables. Once the baseline model was implemented and fully validated by the client, different scenarios were simulated, testing different initiatives in order to obtain optimized oven utilization, higher product throughput, reduce shuttle downtimes, or to study the viability of reducing the number of ovens without impacting production. This is the list of scenarios that have been created. The first one is what we call the baseline scenario. It is used to validate the model with the client. The second one aims to study what would happen if there were no shuttle failures. In the following two scenarios, the arrival rate of products has been increased by 2 and by 5%. In initial ovens 9 and initial ovens 8, the number of available ovens at the beginning of the simulation is reduced to 9 and 8. The next one is the multitasking shuttles, where both shuttles are able to perform loading and unloading tasks. Then, the following 7 scenarios are a repetition of the previous ones, but in this case, the aim is to balance the number of cycles of the ovens. In the last 3 scenarios, it is possible to control the speed of each one of the shuttles separately, or to assign them a different speed each time they are not transporting product. The different scenarios can be parameterized considering the parameters included in the properties menu, and that will update the logic for each one of them. This makes it much easier for the user if he wants to create a new scenario or to change from one to another. As an example, if a user wants to study the feasibility of carrying out operation with 9 ovens, he simply has to change the number of ovens property from 10 to 9. Or if he wants to know how much the product throughput will increase by changing the speed of one of the shuttles, there is also a property so that you can simply change it. As an example, we can change the loader shuttle speed to 0.3 meters per second. From all the scenarios that were created and simulated, the one that brought more benefits and advantages was the one we call multitasking shuttles. Let me copy the scenario's control values to the model to check what's going on in this scenario. Okay, in this scenario, both shuttles are able to perform loading and unloading tasks from or to the ovens. The number of times one of the shuttles have to move aside to make way for another are really reduced. It also increases the utilization rate of the shuttles. Implementing these changes, we can appreciate a service level agreement increase of 65% versus 48.1% in the baseline model, where the service level agreement is the percentage of pallets that are processed in less than 2 hours. Another advantage of this scenario is that while drop-off shuttle will only focus on the ovens from 1 to 5, and the pickup shuttle on the rest, from oven 6 to 10. This will make the number of oven cycles balanced. There are two different ways of running the simulation. The first one is running it using past data. In this case, products arrive according to arrival tables for those specific dates provided by the client. The second one is running it using real-time data. If this method is chosen, the model connects to the customer system and knows at that precise moment if any of the ovens is busy and how much cooking time is left. In this case, product arrive according to semi-interval expressions validated by the client. Additionally to the simulation in SIMIO, and in order to visualize simulation outputs, an exporter was created. And each time a new scenario is simulated, all output data is automatically saved in an SQL database. The Power BI dashboard reads from this database, allowing the user to visualize all results. The first tab gives us an overview of the most relevant information about the cubes, the ovens, the shuttles, or the product backlog. Here we can check the number of processed cubes during the simulation, the average time a pallet is in the system, the arrival distribution for each line, the number of available ovens, the average utilization and time down for both ovens and shuttles, or the average backlog at the beginning of each production line. Then there are some specific tabs with more detailed data for the cubes, the ovens, the shuttles, and the backlog. Regarding the cubes, it is detailed the cube's arrival profile for each day or the time each cube spent in each part of the system. About the ovens, it is shown the average idle time for each oven or the total time down, the number of cycles and failures per oven per day, or the time utilization for each oven. Regarding the shuttles, it is shown their average utilization, their total time down, or the distance they have traveled for the chosen dates. And finally, for the backlog, the customer establishes limits for each line, and the dashboard allows the user to know how many times and for how long these limits have been exceeded. It also allows the user to compare two different scenarios to study which one brings more advantages to the operations. As an example, we can compare the baseline scenario versus the scenario where the arrival rate of product is increased by 5%. In this particular case, it can be seen that although the number of processed cubes increases, the average time spent in the system is much higher. It also greatly increases the time in which the backlog limit set by the customer is exceeded. So, as a conclusion, one could say that this is not the best scenario to implement. The dashboard also offers the user the possibility to compare up to 7 scenarios at the same time. In addition to all simulated data, the dashboard has a second completely separate part that displays data directly collected from sensors placed through the plant. This data gives us visibility on the cubes, the ovens, or the shuttles, allowing the customer to trace the improvements implemented by choosing a new scenario and bringing it to reality. And that's all. Thank you very much. Now we'll be happy to answer any questions you might have. Thank you.
All right. Thank you, Maria. And thank you, Guillermo, for the great presentation there. We do have a lot of questions from the audience here, especially around the model setup and building the model. So we're going to start with those. So first, it seems like, there's a lot of data that was built into the model. Was a lot of that data provided by the customer at first? And how much work was required to really get the data ready for the model?
Okay. Although most of the data was provided by the client,
Mhm.
we also have to do a lot of cleaning task and analysis of this data because actually they didn't know the how much data they had or the quality of the data they had. So we had to do a lot of work in this part.
Great. Okay. Maria, anything to add to that?
Yeah, I would just say that the model is fully data driven. So all the input tables that you see is data coming from the client. At the first stage, as Rodrigo was not Rodrigo, sorry, Guillermo was mentioning, we got the data from the client and we cleaned that and we worked with extracts, let's say. And then as a second step, we like kind of connected the model, the simulation model directly to their system, so it could be fed directly from the data that they had on their systems. But yeah, it was quite of a big part of the project to clean all the data and to put it ready, let's say, and in the structure that we needed for the model to work.
Okay, great. I think that transitions well into this next question we have around running the model in real time. And I think you answered a little bit of this, but how was the model set up to really be able to even run in real time using real time data, and how often is the client using the model?
Okay, as I explained, there are two different ways of running the simulation. If they can run it using past data. So, for example, for the arrival products, they provided us some arrival tables. And the other way to run the simulation is in the future or we will say from the present. In
Hmm.
that case, the model connects directly to their systems with some sensors placed around the plant, and they can read at that precise moment um, how many of the ovens are in that moment processing product, and how much time is remaining for that process.
Okay, great.
Yeah, I would say here that the model was kind of in between, let's say, on a tactical and operational level. So they
Mhm.
will not be running that every minute to get the exact, let's say, operations for each oven and so on, but rather to test different scenarios. And so it was used quite often, I would say, but not to get the detail that they would need for the operators or for the different machines to work and obtain, let's say, the full schedule for that. So yeah, the idea was to run different scenarios and test different initiatives that they might have in the coming future. So I would say it is between the operational and tactical level. That could be, yeah, the model could be used like that.
Great. Yeah, that's great context. Thank you for that. Okay, so we have one on more on the model structure itself. It says it seems like you're using cranes to transport the products from oven to oven. Can you explain a little bit why you chose to use that object versus a different SIMIO object, like a conveyor belt or maybe just a traditional vehicle?
Actually, when we started modeling the simulation, we started using the basic vehicle object, but we realized that it was not going possible to run the simulation or to mimic the reality using the vehicle, because the the main characteristic of this model is that the two cranes cannot crouch never each other. So actually, we spoke to some of the senior colleagues, and they suggested us to use the crane objects because it was going to be much more easier for us to mimic the reality and to run the simulation.
Okay, yeah, just to clarify, so it was more like the bumping logic that
Yeah.
really drove the use of the conveyor or the cranes. Great. Okay. I guess, can you describe a little bit about the connection to Power BI, and I guess how you're visualizing the data? So, first, this one is more, you know, aside from exporting and visualizing via the Power BI visualizations, did you use any of the Simio visuals like the Gantz or any dashboards to, kind of get started or display the model results?
Yes, actually, we use some of this dashboard as, but they were really basic dashboards, only to compare, for example, the sum of product backlog that was accumulating at the beginning of each of one of the production lines, to compare them with the numbers that the client provide us in order to validate the model. It was one of the dashboards we used. But
Okay.
the main visualization we did it inside Power BI.
Yeah, and actually, it was a requirement from the client
Mhm.
that we use Power BI as a visualization software. They had that on their systems already, and so they wanted to use in this particular case this software. So that's why we build the whole visualization of inputs and outputs of the simulation in Power BI.
Great. Okay. Can you explain a little bit about how you connected the model, to how you were able to connect the model to Power BI? Did sorry, yeah. Did you write the Simio results to like a database that I guess was fed the Power BI was fed from?
Yes, exactly.
Okay.
We created a exporter, and whenever you run a new scenario, all of the data is exported to an SQL database, and the Power BI, whenever you refresh the Power BI, it reads from this database.
Okay. All right, I've got just one more question for you all here. How were the what if scenarios that you discussed intended to, improve the model? Can you describe a little bit about the KPIs that you were using to compare each scenario, and then ultimately led to, I'm assuming like a recommendation from the model?
Yes, sure. Um, The client was really focused on different resources utilization rates. For example, the utilization rates of the shuttles. They, of course, they were thinking about the product throughput for each line, and they also wanted to reduce the amount of time each one of the shuttles were idle, were not working. So, for example, with this multitasking shuttle scenario where both of the shuttles are able to perform the loading and unloading tasks from or to the ovens, this amount of time where the shuttles are idle or the amount of time they are spending moving aside to to leave to leave free space to the other shuttle is greatly reduced.
Okay. All right. Great. Well, like I said, that was all the questions we have. So I just want to thank you all for the great presentation, and thank you for being a part of the SIMIO Sync conference.
Thank you, Ryan.
This concludes this presentation. Please click on the back button to access the next presentation.